Okay, so our next talk will be on high-performance machine learning and deep learning with MVAPICH2, which will be a joint talk by Dr. Aamir Shafi and Aarpan Jain. As a bio for Dr. Aamir Shafi, he is currently a research scientist at the Ohio State University, where he is involved in the high-performance big data project. Dr. Shafi was a Fulbright visiting scholar at MIT, where he worked on the award-winning Silk technology. He received his PhD in computer science from the University of Portsmouth in the UK in 2006. Dr. Shafi's current research interests include architecting robust libraries and tools for big data computation with emphasis on machine and deep learning applications. He co-designed and co-developed a Java-based library, MPI-like library called MPJ Express. And the second speaker for this talk is Aarpan Jain. Aarpan Jain received his Bachelor of Technology and Master's in Technology degrees in Information Technology from ABV IIITM, India. Currently, he's working towards his PhD degree in Computer Science and Engineering at the Ohio State University. His current research focus lies at the intersection of high-performance computing, HPC libraries, and deep learning DL frameworks. He's currently working on parallelization and distribution strategies for large-scale deep neural networks. This is DNN training. He previously worked on speech analysis, time series modeling, hyperparameter optimization, and object recognition. He actively contributes to projects like HiDL, MVAPICH2 GDR software, and LBANN deep learning frameworks. So let's welcome our speakers.
Thank you, Mustafa. Right, so today we'll be talking about how we are supporting machine learning, deep learning, and data science with MVAPICH2. So I don't go into the details of this, but machine learning, basically, if you just look at this figure, AI is basically the bigger umbrella of technologies, and within that we have the classic machine learning, which has been around for a long time, but recently, there is a lot of interest in deep learning, and we are also interested in seeing how we can basically support these different technologies using MPI in general and MVAPICH2, specifically. So some of the key algorithms that we use in machine learning and deep learning today, they have been around for a long time, and this is basically the purpose of this particular slide. But obviously, after 2010, because of the emergence of parallel hardware, specifically GPUs and cluster of GPUs, we have been able to make very good progress in artificial intelligence and deep learning in particular. So in the first, part of the talk, I will talk about machine learning and how we are basically supporting that. And after that, I will hand it over to Aarpan. He will talk about how we are supporting deep learning, and out towards the end, I'll come back and talk about how we are supporting data science using MPI. So when we talk about classical machine learning, we basically, roughly speaking, divide this into three categories: supervised learning, unsupervised, and reinforcement learning. The purpose of supervised learning, as most of you would know, is that our algorithm or solutions are trying to learn from the data. In unsupervised learning, there is no input data to teach our algorithms. And in reinforcement learning, we basically are trying to learn from the environment. There are agents involved, but they're trying to learn from the environments. Some of the frameworks that classical machine learning are basically some of the frameworks that support classical machine learning are as follows. The most popular one is scikit-learn. The disadvantage of scikit-learn is that it does not have support for GPUs. And this is for good reason, because the conventional wisdom has been that the classical machine learning algorithms, they are not very compute intensive. But because of the emergence of huge amounts of data and these classical machine learning algorithms are processing today, it makes perfect sense to use accelerators and advanced HPC technologies for not only neural networks but also for classic machine learning algorithms as well. So scikit-learn, if you're trying to write a classical machine learning model or algorithm, scikit-learn would be your first choice. Scikit-learn has been around for more than 2 decades now. And then towards the bottom, we have this cuML. So cuML is trying to fill that gap that scikit-learn has. So cuML is from NVIDIA, and this basically provides support for classical machine learning algorithms on GPU. So the goal of cuML is to stay API-wise stay very close to scikit-learn. So the same application should be able to run on GPUs as well. And recently, we have also seen emergence of other specialized ML libraries like SGBoost. So basically, this supports gradient boosting algorithms. And when we talk about having support for parallel and distributed computing in these different technologies, so scikit-learn also has support for this. It has its own library called joblib. So that can be used for parallel and distributed execution on CPUs. XGBoost is capable of running with Dask, Ray, Yarn, and Apache Spark. And cuML is obviously supported by NVIDIA's Nickel communication library, Dask, and UCX. So I will come back to cuML and talk a little bit more about cuML. So all of these different parallel and distributed solutions that we are going to talk about, and this actually includes some of the solutions that Aarpan will also be talking about, require some kind of communication support from the underlying communication library. So and one of the most frequently used communication primitive obviously has been around MPI all reduce. It has been implemented in the MPS standard for a very long time now. But some of the more specialized deep learning communication libraries like Nickel, for example, they're also supporting this particular primitive. And some of the solutions that we are going to talk about in this talk will obviously be relying on these primitives. So this slide, you have seen this several times today, so I will not go into details, but obviously some of the solutions that we will be presenting today will make use of the MVAPICH2 library. So when we talk about machine learnings, I think the talk is not complete without talking about k-means, and that's what I'll do as well. So on the right-hand side, if you see, this is basically a 2D graph where we have the input points, and the task given to this machine learning model is to divide this into k clusters, and the value of k here is basically 3, as you can see with red, blue, and green colors. And the way this algorithm works is that first of all we initialize the centroids. So if you look at the left-hand side of this slide, step 0, this is basically we are trying to initialize the centroids. And what are centroids? So we are supposed to come up with 3 clusters. So each cluster is going to have a center, and centroid is basically what we are calling basically the center of a cluster. And in this case, when we start the simulation, the cluster is assigned in randomly, right? And then the second step is, which in this particular case is step 1, because we are starting from 0, is that we are dividing the data points, right? So if we are going to run this algorithm on, let's say, 4 GPUs, 2 GPUs, we need to divide these points into, for these 2 or 3 GPUs. And then step 2 is that we assign the elements. And by assigning the elements, we are going to basically now find out which input data belongs to which cluster. We do this by calculating the distance between the point to all the centroids available, and whichever one is the closest, we basically assign our data point to that particular cluster, and that happens because we're assigning the color. And after that, we basically do another compute, which is update the local cluster mean, but the local knowledge is not good enough. We need to do a global mean that we achieve in step 4, and we basically keep repeating step 2, 3, 4 until we reach convergence. And convergence here means that the centroids are not moving anymore, or they are moving by a very small bit that we don't care about. So if we look at the solution of this, I mean, this is another view of looking at the same algorithm. So we are starting off, if you focus on the right-hand side figure, so we are starting off with set of input elements. We are dividing this into, the number of processing elements that are available to us. Step 2 is assigning all local elements, computing the local mean in step 3, and then basically engaging in all reduce. And after that, we basically do a global cluster mean. So the all reduce here is basically not exchanging the whole data. It's only exchanging information about the centroids. And centroids are basically are dependent on what is the value of k. So in this case that we have seen, the value of k was 3. So we might only be communicating like 3 times 3, 9 floating point numbers, which is not a lot of communication. So we obviously expect very good speedups for k-means algorithm because we are not exchanging large amounts of data. And if you see, the k-mean results are, so these are some, results on the right-hand bottom side. So you would see that, x-axis here is the number of MPI cores. Y-axis here is the execution time, and execution time is essentially, coming down as we increase the number of MPI cores. And these are actually, scaling perfectly. And the blue, green, and red lines basically belong to different dimensions of the problem. So 32, 64, and 128. So now let's talk about the QML library. So the QML library comes from NVIDIA's RAPID project, and the goal is to basically, maintain end-to-end data science pipeline on the GPUs, right? So today, if you're talking about deep learning pipelines or big data pipelines, we are able to do a lot of computes on the GPUs, but for data loading and for intermediate results, sometimes you have to go back to the disk, or you need to store the data on the CPUs, right? So that's essentially a big overhead. If it's possible, if the data can fit in the GPUs, so they should remain on the GPUs as much as possible. And basically, some more facts about the QML library. This is a GPU accelerated library. It's a GPU counterpart of scikit-learn, and it supports so-called multi-node, multi-GPU systems, which means that you're able to utilize multiple GPUs in your node as well as scale out whenever required. So the right-hand side is basically the architectural view of the QML library. So starting from the top, we have the Python layer, because a lot of people like to do these kind of stuff in Python. And then below the Python layer is basically algorithms. So the QML folks, they are taking algorithms one by one, and they are adding that to the QML library. And down at the bottom, we have the primitives layer. So if you have, I mean, it's possible that you might require an algorithm which is not supported. So you can just work directly with the primitives and try and come up with the implementation of the algorithm yourself. So in the vanilla QML version, the support for parallel and distributed computing is provided by Dask sitting on top of UCX. And for collective communication, Nickel is being utilized. So what we have done in what we call MPF for QML, which is currently in 0.1 release, and it's available from our website, is that we have introduced, we have added support for MVAPICH2 GDR, using MPF for Python library. And these are some of the results that we have seen, and these were published in our ML HPC workshop SC 2020. And I will just talk about the results on the top left, which is the k-means algorithm. So x-axis is number of GPUs, y-axis is training time. Lower is the better, and the black worm is essentially plotting the speedups compared to Nickel. So MVAPICH2 GDR compared to Nickel. And as you can see, for 32 GPUs, we are seeing around 1.6 times the speedup. So nothing is changing. The only thing which is changing between the yellow bar and the red bar is the communication library. So with this, I will now hand it over to my colleague, Aarpan.
Okay, thank you, Aamir. Audible, right? Okay, great. So now let's talk about the most revolutionary subset in any area. That's deep learning. So deep learning is a subset of machine learning, we all know, but nowadays deep learning is more popular than machine learning. Sorry, Aamir. So now let's talk about deep neural networks, what they are. So you can imagine deep neural networks as a mathematical function which is mapping input, okay, I'm not sure, okay, which is mapping input to the output. Okay, so it's a very, very complex mathematical function. It consists of several smaller mathematical functions that are called neurons. And what is a neuron? So neuron is just a weighted summation of all the inputs. And then we apply our activation function to introduce nonlinearity. So this is a very high level introduction of deep neural networks. Let's see how we train it. Just like K-means, deep neural network training is also iterative. So basically, we give input at the input layer, and then we apply all of these functions in a sequential manner. So basically, we have a layer, and we have several neurons in it. We will apply the neurons in that layer to compute the output of that layer, and we will do the same thing again and again till we reach the output layer. Okay, so once we reach the output layer, we will get the prediction from the deep neural networks. But at the starting, the prediction will be wrong because this neural network is not trained for your application. So that's why we are going to compare it with the actual output, and then we are going to compute the error. After getting the error, we are going to backpropagate it to all the layers, and this is called backward pass. So as you can see that deep neural network training is a sequential task, or in a way it is a sequential task. You process layer one by one, both in forward and backward pass. So let's see what are the important concepts when it comes to deep neural network. Why I'm discussing these concepts here? Because you are going to change these hyperparameters when you are doing distributed training. Let's talk about the learning rate. You can assume or you can think learning rate as a parameter which scales the way you learn new things, or with how much quantity or what quantity you are going to improve the deep neural network. So let's say on the y-axis we have error, and on the x-axis we have a parameter. When we change the parameter, the error will change, and we want to find the global minima. So if your learning rate is too high, you may overshoot and reach to a different end. You don't want to do it. In the same way, if the learning rate is too low, you will take very, very small steps, and it will take forever to train that model. So that's why we want the learning rate to be just right. Learning rate depends on your application, data set, and the batch size. So what is the batch size? So there are different ways to train deep neural networks. The first way is to just take all the samples in the data set, do forward and backward pass, and update the weights. This is called batch gradient descent. Another way is to take one sample, do forward and backward pass, and then update the weights. This is called stochastic gradient descent. Both approaches have some disadvantages, like in the batch gradient descent, we are going to wait, or we are going to process all the samples in the data set before updating the model once. This will be very time consuming because state-of-the-art data sets have like 1 million or millions of samples. On the other hand, if you look at the stochastic gradient descent, it is just considering one sample. This is also not good because you won't be able to use all of your codes. So that's why we have something in the middle called mini batch gradient descent, where we take a subset of samples, do forward and backward pass, and then update the weights. So this is called mini batch gradient descent, and finding the optimal batch size will give you the best learning rate or the best learning for the deep learning. So now let's talk about distributed deep learning. It all started when Alex Krasowski in 2013 or around that time proposed AlexNet model. He showed that deep neural networks can actually achieve better accuracy than the machine learning model or the statistical modeling. So at that time also, he was using 2 GPUs to train the model. The model was so big that he cannot train it on a single GPU. This story is true for all the state-of-the-art models that have been proposed over the time. So be it AlexNet, ResNet, NASNet, or AmoebaNet. From 7 layers in AlexNet model, now we are at thousands of layers in the AmoebaNet model. And all of these state-of-the-art models cannot be trained on a single GPU or a single processing element. So that's why we need multi-GPU training. However, there is a limit. You cannot have thousands of GPUs in one node. So there is a limit to the scale up. So that's why we need scale out. Okay. Let me just use this one. Okay. So now let's dive into distributed training. Broadly, the parallelization strategies or the way to do the distributed training can be divided into 3 categories: data parallelism, model parallelism, and hybrid parallelism. As the name suggests, data parallelism distributes the data, model parallelism distributes the model, and hybrid parallelism combines data and model parallelism. So in this talk, I'm going to cover all of these 3 strategies. So let me start with the data parallelism first, as it is one of the most popular and very easy to use parallelization strategy. So as I described earlier, distributed or the deep neural network training is an iterative process. So in data parallelism, we are going to replicate the model, or we are going to copy the model to all the GPUs or the processing elements. So let me take an example. Let's say we have 4 GPUs. We are going to replicate or copy the model to all the 4 GPUs. One second. Yes, to all the 4 GPUs. And then we are going to distribute the data. So let's say you are using 128 batch size. So you are going to give first 32 samples to GPU 1, GPU 0 in this case, next 32 samples to GPU 1, and so on. You will do the forward and backward pass simultaneously on all the GPUs. At the end of the backward pass, you will have local gradients. Why do we have local gradients? Because we are using different samples. So that's why we need MPI all reduce operation to get global gradients and train only one model, not 4 different models. So after using MPI all reduce, we will get global gradients on all the GPUs, and these gradients can be used to update the weights. See, it is very simple. Yeah, on paper. So now we have some basic understanding of deep learning. We already, yes, one second. So go on.
So if we use data parallelism to do the training, will we end up with the exact same weights, like the model state, as if we're doing sequential training, given that we have the same effective batch size? And like,
yes, if we have same batch size, we will end up with the same model, same sequential model, as long as the batch size remains same. If you are changing the batch size, you will not get the same model. Okay, thank you for your question, Norris. Now let's go to the deep learning solutions. We have some basic understanding of deep learning. We already know MVAPICH2 and MPI. So let's see what amazing things we can do when we use MVAPICH2 in distributed training. So I have divided this section into two categories, data parallel training and model parallel training. In the model parallel training, I am going to discuss hybrid training also. So we propose a MVAPICH2 or the MPI-driven infrastructure for MLDL training, where you can use TensorFlow, PyTorch, and MXNet on the top of Horoword to do the distributed training or the distributed data parallel training. If you are doing it on CPUs, you can use MVAPICH2X to get the best performance. Otherwise, you can use MVAPICH2 GDR for GPU training. If you don't like Horoword, that's fine. We have distributed data parallel training support in PyTorch and TP-Speed, so you can also use those libraries to do the distributed training, and you can use MVAPICH2X for the CPU training and GDR for the GPU-based training. So how can you do it? Let me just give you an example. Once you have installed PyTorch, TensorFlow, or your favorite deep learning framework, you can, on CPUs, you can easily install Horoword or configure Horoword with MPI by using this line. It is as simple as this. Okay, you have to load MVAPICH2 if you want to configure Horoword with it. If you want to do it using MVAPICH2 GDR, you just have to specify that for the GPU already used, you are going to use MPI and give CUDA path, and that's it. And don't forget no cache there. It will bite you if you don't do it. Okay, so what kind of performance you can expect when you're using MVAPICH2 GDR? So this is a sequential training run where we are running ResNet 50 with a batch size of 64 on a single V100 GPU. If you do it, you will get around 334 images per second. What is this? This is a throughput, okay? So we are processing around 334 images per second on V100 GPUs. If we use the distributed training, we can process up to or around 632 images per second. That's like 1.89 or 1.9x. And when you add more GPUs, you will get near linear speed up. This is just the overhead of implementing distributed training when you go from one node to from one GPU to two GPUs. So in distributed deep learning, we use large-scale all-reduce operations. Typically in HPC applications, we have very small messages that can be like from 4 bytes to 1 MB. But when it comes to distributed data parallel training, the message size can go up to 64 MB, 64 megabyte. That's a lot of data. So that's why we have to optimize MVAPICH2 for those large messages. And as you can see that we are able to get good performance on the small messages, and we are able to get similar performance with the MVAPICH2 when compared to nickel. So you have distributed training and you have all the things. Yes, go ahead.
So the reason is that deep learning has the larger message sizes. Why it is more larger than HPC application?
Yeah. Okay, thank you. That's a very good question. Why do we have large messages in deep learning? The reason is the number of parameters. We have very, very large models. So that's why, and in all reduce operation, we are going to reduce those parameters or the gradients. And the size of the gradient is equal to the size of the parameters. So that's why we have very large message size in deep learning. I hope I answered your question.
Yeah, thank you.
Yeah, thank you. So you have done distributed training on 2 GPUs. Wow. What's the big deal? So what can you achieve with the distributed training? Let's see that. If you have 1500 V100 GPUs, you can get up to 0.42 million images per second. That's like 30% of ImageNet data. You can just process 30% of ImageNet data in just 1 second. If we do a quick math, then each epoch will take only 3 seconds, and you can complete the entire training for ResNet 50 model in just 4.5 minutes. We have all heard that deep neural networks take weeks or the months to train. But if you have enough resources, if you have enough GPUs and your communication runtime is optimized, you can get really, really good performance. Yes? Can you please repeat your question?
What is the percentage of communication time for each epoch in the previous?
So in data parallel training, we try to overlap most of the communication with the compute. So the communication to compute ratio will not be will be around 5 to 10% at most. And it depends on the model and other things. So it's variable. GPUs are good, but can we do the same thing using CPUs? So we did the similar study on the tech Frontera and on 2048 CPU nodes, and we can achieve up to 260,000 images per second. That's like, if you do the same math for this one, you can train ResNet 50 model in 7 minutes. Yeah, it is more than 4.5 minutes, but this is still good. You can do it on the CPU. We have all heard that CPUs cannot be used for distributed training or CPUs cannot be used for deep learning. No, you can train it on CPUs. So with that, I move to the model parallelism. Like the data parallelism is really useful when your whole model fits inside the memory of a single processing element or a GPU. So all the parameters has to fit inside the memory of a single GPU. But if you have a very large model like GPT-3, which cannot fit inside the memory of a single GPU, you have to use model parallelism. And what kind of things you can achieve using distributed training by combining it with MVAPICH2. Let's see. So let's talk about the CPU first. As you can see in this figure, that you can easily go out of memory if you are using larger image size. And so basically, if you want to train ResNet 1K model, that's a very, very big model, on 512 image size or the 700 image size, 700 pixels image size, you cannot do it even on a CPU. So how can you train such models? So that's why we proposed Hyperflow, which is like a hybrid training that uses layer parallel training. Basically, distributes the layer at the level of, distributes the model at the level of layer on multiple GPUs or CPUs, and uses pipeline parallelism to overlap some of the compute by dividing the batch size into micro batches. We improve the performance by combining data parallel training with the pipeline parallelism. And this is just an overview of that system. And if you want to know more details, just go to this paper, which was published in ISC. So this is the kind of performance you can get when you use MVAPICH2 using in Hyperflow system. So we evaluated this system on 512 nodes on the tech Frontera, and we were able to get near linear speed up. The scaling efficiency is like 98% on 256 nodes, or the 94% for 512 nodes. So this is the kind of a performance you can get. Now let's move to the GPUs. Everyone is training deep learning models on the GPUs. So we tried to solve the similar problem on the GPUs. We found that if you want to train your model on the larger images like 1000 by 1000 pixels. Okay, let me ask you a question. If you take a picture from your phone, iPhone or Android, what is the size of that image? Can anyone answer it?
About 3 megs.
3?
About 3 to 4 megs.
Yeah, 3 to 4 megs. But like, I mean, what is the height and width of that image in terms of pixels?
Around 4K resolution.
Yeah, 4K. What is the size of the 4K? 3000 by 4000 or something like that?
Yeah, just about.
And we are still training our deep learning models on 256 by 256 pixels. So can we train our models on such large images? Yes, so that's why we proposed this system called GPU-enabled memory-aware model parallelism system at the supercomputing conference. So here we identified that between the training steps, we have both memory and the compute available. So can we use that memory? So if you want to know about the design and other things, please go to this link and you can get more information. So what can we do with such system? So we have application from the pathology. So that's why we try to exploit model parallelism in the AI-driven digital pathology. In digital pathology, we have 1000 pixel, like 100,000 pixel by 100,000 pixel images. Obviously, you cannot train your model on such large images. But if you use the tiling-based method and try to train your deep neural network on those, the tile size will be restricted because of the GPU memory. They were limited to just 256 pixels. And the smaller tiles will lose the structural information because you are zooming in too much. So can we increase the tile size and reduce the training time so that you can do more experiments and train a better model? So by using our system, like if you just use the traditional layer parallel training or the model parallel training, it will take around 7.25 hours to train that model on 4 GPUs. We brought it down to 4.21 hours on the same number of GPUs. And to show the scalability, we train it on 128 GPUs in just 27 minutes. So that's the kind of a performance benefit you can get if your communication runtime is optimized. If the communication overhead is less, you can propose better parallelization strategies. You can better decompose the problem. So with this, I conclude the distributed deep neural network training and hand it over to Aamir. Yes.
Yeah, in some cases, other than all reduce, there are other operations collective that are used, like reduce scatter or all to all.
Yes.
Can you say when are these used instead of all reduce or in addition?
Okay, yeah, thank you for your question. This is a very good question. So basically the question is, when do we use other collectives in distributed deep neural network training, right? So in data parallel training or in the data parallelism, we mainly use all reduce, but when it comes to the model parallel training, we use all kinds of collective operations. For example, in layer parallelism, we use point-to-point operation as well as all reduce operation. In subgraph parallelism, we use all gather operation and the scatter. In deep speed, we use all-to-all operation. So it all depends on how you want to parallelize your training. Did I answer your question? Okay, thank you.
So in the last part of this talk, we are going to talk about data science. So Anne has a question, so let's take that one.
Sorry. So, for example, if we use the ResNet 50 that fits to the some kind of program, when compared to the model parallelism and data parallelism, which one do you think the better? Because, for example, of course, for example, resonant 1001, we must use the model parallelism, but for the resonant 50, which one is will better?
So if you are doing training using ResNet 50 and your input or the data sample size is small, by the data sample size I mean the width and height of your images, then you don't have to use model parallel training. Data parallel training will give you the best performance in terms of throughput. But if you really want to restrict yourself to a certain batch size, then only you should go to model parallel training, like in case of strong skill.
Okay, thank you.
Yeah, thank you.
So I'll now talk about the data science part of the talk. So the technology that we are presenting here as a use case is Dask, which is a popular task-based distributed computing framework in Python. So it lets you scale your Python applications from laptops to high-end systems. So it's the same application that works on the laptop will work on HPC systems as well. Under the hoods, Dask scheduler is going to convert your application into a task graph, which is then executed lazily on parallel hardware. So if you download today, Dask today, you will basically get two communication devices. One is TCP, and the other one is basically UCX. So the support for UCX has been added by NVIDIA, obviously, and so we will see what we have done in this for this technology as well. So today, if you're writing a data, if you're working with data science, there are two, the two most popular options available are Dask and Apache Spark. So this is the execution model of Dask. So basically everything starts with a scheduler. So if you're working on an HPC system, you would bootstrap a scheduler, and then the workers can come and go, and they will basically get added to the scheduler, and together the scheduler and all the available workers, they become a Dask cluster. The user application is submitted through the client, and the client would connect to the scheduler, and essentially your application would then get executed in a parallel and distributed way. So there is a lot of communication going on between the workers, and workers can come and go, workers can talk to the scheduler. So this is an opportunity for us to exploit MPI-based communication here. So what we have done here is that, by default, TCP and UCX are available as communication options. What we have done is that we have added support for MVAPICH2 based communication backend that we call MPF or Dask. And this is how essentially it looks like. I will just focus on the middle part here, which is called Dask distributed, because this is the part of Dask which is adding support for parallel and distributed computing. It provides the notion for things like scheduler, worker, and clients. The communication layer, TCP and UCX are already supported, but what we did was those yellow boxes. So MPF for Dask sits on top of MPF for Pi, that sits on top of MVAPICH2 GTR. These are some implementation details that I would skip in the interest of time. What basically I'm trying to say here is that we utilize a project called Dask MPI, and Dask MPI essentially lets you bootstrap Dask execution using MPI launchers. Similarly, one of the challenges that we had to tackle while doing this work was to implement point-to-point primitives as Python coroutines, right? So these coroutines are essentially different than the kind of normal functions that we are used to writing, because if these communication coroutines, if they are IO bound, they need to somehow relinquish the CPU to other coroutines. So for example, if you look at the pseudocode on the left hand side, in this you would see that we are calling this function called async io.sleep. The argument here is 0, right? So we have non-blockingly sent the message, we are testing it, and then in the loop we are testing it. You would not do this, you would not have this sleep in a typical HPC application, but it was needed and required in this case because we need to relinquish the CPU for completion of other communication operations. So here we basically just outline the steps that you have to do while working with MPF or Dask package. And in this case, basically the main steps are that, we have to install mini-conda, and then we have to install libraries, modules, depending on, if this is a GPU-based execution or a CPU-based execution. You would basically go and install MVAPICH2. You can go with any of the MPI library, so like X or MVAPICH2 or the GDR, and then install MPF for Pi, Dask MPI package, and then our MPF for Dask package, and then you should be good to go. So some of the results that we have seen essentially are very encouraging. So for example, this is one benchmark called cupy array and its transpose. So if you're working with Python arrays, so NumPy is a very popular library. But NumPy only works for CPUs. So if you want your GPUs to be stored on, if you want your arrays to be stored on the GPU and be processed there, so you would typically work with libraries like cupy. So in this case, what we are doing is we are taking a transpose of the cupy array and making adjacent elements. We are simply adding the adjacent or corresponding elements. So in this case, on x-axis, we have the number of Dask workers going from 1 to 32 GPUs. X-axis is the total execution time, and we are basically plotting TCP, UCX, and MPF for Dask. And as you can see, the red bars are actually doing better than UCX. So in this case, this is doing 1.7x better than UCX. So this is available as an open source software. So we are currently in 0.2 release, and more results can be seen in our paper that was published in CC Grade 2021. So with this, I would conclude the talk that we have seen. So basically in this talk, what we have reviewed is how we are supporting machine learning, deep learning, and data science using the MPI communication layer in general and MVAPICH2 in specific. And if you would like to talk about these things in more detail, so Aarpan and I are available. So feel free. Thank you.